Assalamualaikum warahmatullahi wabarakatuh, and a very good day. So this is topic 2, electromagnetism, under the subtopic of core losses. Okay, so in previous lesson, what we have discussed is that you have been introduced on the usage of what called electromagnetic circuit. Okay, and so today we will continue on what we call losses, okay, inside the magnetic circuit. So actually there are several losses, okay, that associate with this magnetic circuit, but for this syllabus we only concentrate on which is what we call core losses, okay, that the losses that actually occur inside the core. Okay, inside these core losses, so we have two different losses, which is what we call the hysteresis losses, okay, due to the hysteresis effect, and these losses is actually proportional to the frequency system. The second losses is what we call eddy current losses. Okay, this one is due to the what we call the current that induced along inside the core. Okay, and it is actually proportional to the square of the frequency. And these two, hysteresis losses and eddy current losses, are regarded as what we call core losses. Okay, so actually we will deal with these two losses in what we call the transformer analysis. So what is actually hysteresis losses? So it is a losses caused by the magnetization and demagnetization of the core as the current flows in the forward and reverse direction. So as you can see in this graph, this is the plot between the flux density versus the magnetizing force. As the magnetizing force, which is right now current, increase, okay, from zero, increasing, magnetized, the magnetic flux is also increased. As you can see, when H is increased, the flux density, which is B, is also increased, okay, to a certain point. But when the magnetizing force is decreased, okay, for example, then actually demagnetized, it will actually, however, the magnetic flux doesn't decrease at the same rate, less gradually. So it will took this part instead of the original part here. So when H is decreased, okay, the B, which is the flux density, is not decreased as equal to decrement of the H. It's actually, it actually decrease less compared to H, and this is actually the new part for demagnetizing. Therefore, when the magnetizing force reach zero, okay, so when H is reached to zero again, the flux density still has a positive value at this point. Okay, so even though when H is zero, so we have what we call flux density inside the core. Okay, so in order flux density to reach the zero, so the magnetizing force must be applied in a negative direction. So actually, the magnetization and demagnetization, and then again magnetization. Okay, so actually the process of magnetization and demagnetization actually produce this what we call hysteresis losses, and the hysteresis loop represent the energy loss during this process. So inside this closed loop here, is actually where we can actually calculate the hysteresis losses. So in general, the hysteresis losses is depends on the volume of the core multiply with the cross section of the core multiply with the frequency. Okay, so since volume and also cross section is usually fixed, so in order to have less losses, you can actually control the frequency of the system. Okay, so if we want to minimize the core losses, okay, you can either actually reduce the frequency, or you can choose what you call a material that having a thin hysteresis loop. For example, A here. The second losses is what we call eddy current losses. So this is actually a natural phenomenon where when we magnetize some materials, okay, when we actually wind out the a material here, and then you are having a current that flow inside the solenoid here, there will be a current, a closed path current that induced inside this core, and this current here, what we call the eddy current. And since this is a current, so and the material also has their own internal resistance, so this will actually produce what we call eddy current losses. Okay, so the eddy current losses can be obtained by using these equations. So how to reduce the eddy current is actually, the first one is to use a highly resistive core material, for example, silicon steel ferrite core, okay, to resist the what we call the production of the internal current inside the material. The second one is to use laminated core. So instead of using a solid core, what we can do is actually to cut the solid core into pieces, okay, and then laminated them and then combine them as a one unit. For example, this is actually the basic structure of the transformer. So this is the core here. So as you can see, instead of using a single core, we actually slice the core into laminated pieces and then combine it again. So this is actually what this is why we do this, is actually to reduce the area of the closed path. Okay. So the calculation of eddy current losses is quite complicated, and usually we can analyze this by using finite element analysis software, for example, ANSYS, Maxwell, and FEMLab. So next is about mutual inductance. So what is induction? So induction is the magnetic field which is proportional to the rate of the change of the magnetic field. And induction also is known as an inductance, which is the symbol is L, and the unit is Henry. So in other words, 1 Henry is defined as the amount of inductance required to produce an EMF of 1 volt in a conductor when the current change in the conductor is at the rate of 1 ampere per second. And there are two types of inductance. So the first one is self-inductance, and the second one is the mutual inductance. So what is self-inductance? So when there is a change in the current or magnetic flux of the coil, an opposed induced electromotive force is produced, which is voltage. And this phenomenon is termed as a self-inductance. So this this statement is actually reflect this, okay? So when there is a change in the current, okay, they will produce what we call electromotive force, which is the voltage. And how it is derived, so based on this statement. So when the current starts flowing through the coil at any instant, it is found that the magnetic flux become directly proportional. So this referring to this equation. Okay, flux is proportional with the current. Okay, and it is given like this, and we know that the flux is equal to the inductance, which is the constant here, which is a constant here, L, multiplied with the I. Okay, and L is termed as a self-inductance of the coil. And L is actually based on these equations. We rewrite again, and then we can find that their inductance L is N, which is the number of turns multiplied with the flux and over the current. And this is what I call the unit is Henry. So this is what we call the self-inductance. L is equal to N flux over I. While mutual inductance is defined as the property of the coil due to which it opposes the change of current in the other coil, or you can say in neighboring coil. When the current in the neighboring coil changes, the flux sets up in the coil, and because of this, changing the flux EMF is induced in the coil, and this is called mutual inductance EMF. Okay, and mutual inductance is actually the fundamental concept of the transformer. So to understand more what is mutual inductance, so let's consider this circuit. There are two coils, coils A and coils B, are placed near to each other. So when the switch S is closed and the current flow in the coil A, okay, it set up a flux in the coil A. Okay, so it set up a flux in the coil A, and an EMF or voltage is induced in the coil A. And if the value of the current is changed by varying the value of this resistance, okay, the flux linking with the coil, okay, the flux that actually link with the coil B also change because of this change of current, right? Because we know that current is proportional with the flux. So if there is a change of current, there will be a change of flux, and a flux that link coil A to coil B, okay, will also change. So this effect will actually also have some change on the EMF induced in this coil B. So this is phenomenon of the linking of the flux of the coil A with the coil B is called the mutual inductance. So how to calculate the mutual inductance? So considering this circuit, so we have two windings here, coil A and coil B, and you should know that each coil has their own self-inductance. Okay, so the self-inductance, as been mentioned before, can be calculated as N, number of turns multiplied with the flux induced inside coil A over the current that flowing inside coil A. And this can also be deduced to these equations. And A square over the reluctance. And you have also the self-inductance of coil B, which is can be also write down as this one. And due to some calculations, which is not shown here, the mutual inductance between coil A and coil B can be calculated by using this equation. So M is actually referring to the mutual inductance, which is equal to square root multiplication of LA and LB. If there is a flux leakage, okay, so we need to put what I call a constant K here, which is the coupling coefficient. So this coupling coefficient can range from 0 to 1. Okay, so when there is no magnetic leakage, so we can set that the K is equal to 1. So, but in general, we are always ignoring the magnetic leakage in our analysis, and always we are using this equation for our analysis. So this is example A. So we have coil A and coil B. So what you need to do is to get the self-inductance of each coil. So LA and LB, and we know that LA equation is the number of turns of coil A over the reluctance of coil A, where the reluctance of coil A you can calculate by using the length of the materials, the core materials, okay, over the permeability of the materials multiply with the cross section of A. And also same, so this is NB over XB squared. So this one also reluctance, which is your LB mu A B. And this LA is actually, this one is actually a circle, okay, where this is your coil A, this one is your coil B. And give this is actually a radius, okay, or the radius, meaning that LA unit is actually by using, calculate by using 2 pi square radius, okay, and this unit must be in meter, not millimeter. So you need to convert into meter, and also the cross section is in meter square, okay, then you can get the answer. And the last subtopic for this electromagnetism is the energy stored in the magnetic circuit. Okay. So if a current increased by change of I, which is delta I ampere in dt, so the induced of EMF, electromagnetic force or voltage, can be calculated as this one. This is actually referring to Faraday's law and Lenz's law. And if you want to find what is the energy absorbed by the magnetic circuit during time delta t here, okay, what you need to do is actually to multiply I, multiply with E, okay, and multiply also with time. So you can got joule, okay, the energy I, which is this one is P, multiply with T, okay. So you will find that the energy is Li multiplied with the change of the current. And if you want to get what is the amount of energy stored inside the inductance when the current is increased from 0 to a value of I, so you need to integrate the current, okay. And finally, the energy stored, okay, inside an inductance, inside an what I call the magnetic field, is actually can be calculated by using this equation: 1 over 2 multiplied with the inductance value I squared, okay. And for further applications, so since we know that the inductance is actually derived from here, right? Okay, so you can actually use this equation where we can actually have to expand this to this equation. So actually the energy stored, the inductance, is actually depends on the permeability of the materials multiply with the magnetizing force of the materials, and then also multiply with the cross section and the length of the materials. So I think that concludes on the electromagnetism subtopic, okay, under topic 2. So next we will go on the transformer. So thank you very much.